For over half a century, Moore's Law was the undisputed holy grail of the tech world. But today, it's officially hitting a brick wall. When you shrink transistors down to a single nanometer, you're literally dealing with a boundary just 10 atoms thick. At that point, classical physics completely breaks down, and quantum mechanics takes over. Electrons start leaking right through microscopic barriers, even when the chip is totally idle. The result? Mind-boggling amounts of wasted energy and temperatures that turn modern processors into microscopic furnaces. And to survive this wall, the global semiconductor game is splitting into a high-stakes geopolitical battle. The US and its allies are betting everything on multi-million-dollar EUV machines and 3D chiplets. China is pushing the limits of older DUV technology, particle accelerators, and nuclear power to dodge Western sanctions. Russia is retreating to rugged military-grade silicon. And Japan, they're aiming for a 2-nanometer leap while pioneering photonic chips, computing powered entirely by light without the heat. How is this global chip war actually playing out? And what technology will power the next 50 years of AI? Let's break it down. 1. The US and Western allies. High-end EUV and the chiplet play. The US, along with key players like ASML, TSMC, Intel, and Samsung, is pushing physical limits with ASML's new high-end EUV systems. We're talking about $400 million machines here. Intel actually jumped the gun early, grabbing the first wave of these giant tools to target its 1.4 nanometer node. At the same time, building a massive single-piece chip at these microscales is insanely expensive and yields tons of defects. That's why the US led the UCIe alliance to standardize chiplet technology, basically breaking big chips into smaller, specialized tiles and stacking them in 3D. Geopolitically, through the CHIPS Act, America's goal is crystal clear: bring manufacturing back home and cut reliance on the Taiwan Strait. 2. China, SAQP, particle accelerators, and nuclear-powered AI. On the other side, blocked from buying EUV systems, China turned to a workaround called SAQP multi-patterning. They force older 193-nanometer DUV machines to expose a single silicon wafer 4 separate times just to hit 7-nanometer and 5-nanometer chips for Huawei. Now, let's be real. The economic side of this is brutal. Defect rates soar past 60% and costs skyrocket. But backed by hundreds of billions in state subsidies, Beijing doesn't care. This is a matter of national survival, not market economics. Simultaneously, they're building massive SSMB particle accelerators to create their own domestic EUV light source. To feed these power-hungry fabs and keep massive AI data centers online 24/7, China is rolling out a massive wave of next-gen nuclear reactors, including Generation 4 high-temperature gas-cooled reactors, small modular reactors, SMRs. Bottom line, they're securing zero-carbon baseload power so their AI push won't crash the national grid. 3. Russia, rugged military silicon. Under heavy Western sanctions, Russia isn't trying to build consumer chips for your next smartphone or cloud AI. Their playbook is all about mastering legacy nodes from 90 to 350 nanometers. Think about it. Commercial chips need to be tiny and power efficient, but military hardware for missiles, tanks, radar, and satellites needs to be bulletproof. A 90-nanometer chip handles electromagnetic pulses, cosmic radiation, and extreme temperatures from -50 to 150 degrees Celsius far better than a fragile 2-nanometer node. Russia is also developing maskless electron beam lithography, specifically for off-grid defense tech. 4. Japan, the Rapidas gamble and material monopolies. Japan is playing a clever double game. On one hand, they launched Rapidus alongside IBM to leapfrog straight from 40 nanometers down to a 2-nanometer gate all-around process in Hokkaido. On the other hand, They hold an absolute stranglehold on global chip inputs. Japanese firms control over 50% of the worldwide market for ultra-pure silicon wafers and EUV photoresists. In short, if Japan turns off the chemical tap, global chip production grinds to a halt. No matter what country you look at, every traditional silicon chip is running headfirst into the exact same enemy: electron friction. In conventional electronics, binary data is carried by flowing electrons. But electrons have mass. As you cram tens of billions of them through microscopic copper wires, they slam into silicon atoms, generating intense heat, a phenomenon known as Joule heating. On top of that, modern hardware suffers from the famous von Neumann bottleneck. GPUs spend up to 80% of their total energy doing absolutely nothing, just sitting there waiting for data to travel across slow copper buses from memory. By 2030, AI data centers could swallow up nearly 10% of the entire planet's electricity just to run cooling fans and liquid pumps. We are rapidly slamming into the AI power wall. So how do we fix this? Scientists are making a game-changing move, replacing electrons with photons, particles of light. Welcome to the era of photonic chips. The physics behind this is a night and day difference. First, electrons have mass and create friction. Photons have zero rest mass. They glide through transparent silicon nitride channels via total internal reflection. Zero physical collisions mean zero resistance, dropping heat generation down to virtually zero. Second, while a copper wire carries a single electrical signal at a time, photonic waveguides use wavelength division multiplexing, WDM, meaning you can shoot dozens of different colored light beams through the exact same channel simultaneously without any signal noise. To make this market ready, the tech world is adopting co-packaged optics, CPO, mounting laser modulators and photonic waveguides directly onto the same board substrate as the GPU, killing off copper interconnects for good. Now, because the wavelength of light limits how small you can shrink a photon channel, light won't completely replace sub-2 nanometer silicon logic math. The real future is EPIC, electrophotonic integrated circuits. Ultra-dense silicon handles raw math, while light handles all high-speed data transfer. The future of human computing isn't just about making transistors smaller anymore. It's going to be built on a golden triad. 1. Architecture, 3D, chiplets for cost-effective physical scaling. 2. Interconnects, photonic optics and CPO for heatless, light-speed data flow. 3. Processing models, neuromorphic brain-inspired chips for robotics, alongside quantum computing for nation-scale simulations. At the end of the day, whichever nation masters the combo of light-speed computing and sustainable clean energy will rule the next century of artificial intelligence. What's your take on this global chip war? Do you think light-based computing is the key to unlocking true AGI? Drop your thoughts in the comments below. If you enjoyed this deep dive, smash that like button, subscribe, and hit the notification bell so you don't miss the next analysis. Thanks for watching, and I'll catch you in the next one.